Have you ever gazed at the night sky and wondered what secrets lie hidden among those twinkling stars? Well, today let's talk about a cosmic enigma that has both puzzled and intrigued scientists. A strange object located 800 light-years away has been sending mysterious signals to our planet. But here's the catch. It's not your typical celestial body. It's neither a star nor a black hole. Instead, it's a peculiar object that seems to be bombarding the Earth with an unexpected payload, antimatter. You might be thinking, antimatter? That sounds like science fiction. Well, here's where things get even more interesting. Welcome to the fascinating world of astrophysics and particle physics. Imagine a universe where matter and energy can be transformed into one another, where the tiniest particles hold extraordinary powers. That's the realm we're about to explore. But before we delve into the heart of this cosmic mystery, allow me to introduce myself. I'm your guide to the cosmos, here to unravel the complexities of the universe and bring them to your fingertips. So buckle up and prepare to embark on a journey filled with mind-bending concepts, distant galaxies, and the relentless pursuit of knowledge. And now, without further ado, let's dive into the intriguing phenomenon of a star showering the Earth with antimatter. Picture a massive star nearing the end of its life. As it collapses under its own gravity, it transforms into a compact object known as a neutron star. Neutron stars are renowned for their extreme properties, including incredibly strong magnetic fields. Some of these neutron stars rotate rapidly, making them true cosmic engines. And it's precisely these rapidly spinning neutron stars that hold the key to our story. They are known as pulsars, and they can accelerate charged particles like electrons and positrons to incredible speeds. Now, let's turn our attention to the star in question, Geminga. Located about 800 light-years away, Geminga is a young pulsar, relatively small in size and shining brightly against the backdrop of space. You might wonder how we know these details. Well, thanks to the powerful instruments aboard the European Space Agency's XMM Newton Observatory, we've been able to study Geminga in great detail. These observations have provided valuable insights into its behavior and characteristics. But what's truly remarkable about Geminga is its ability to accelerate particles to astonishing speeds. As the pulsar rotates, it releases beams of radiation, which when observed from Earth, can appear as pulsating signals, hence the name pulsar. However, Geminga is not your typical pulsar. While many pulsars slow down over time, Geminga remains remarkably fast. It spins at a dizzying rate of 67 rotations per second. To put that into perspective, if Earth were to spin at the same rate, a day on our planet would last only 9 minutes. But Geminga's rapid rotation comes at a cost. It loses rotational energy at an impressive rate of 2% per year. Where does this energy go? Some is emitted as light, but a significant portion goes into accelerating particles. Geminga blasts a substantial number of positrons into space. In fact, our Sun produces around 10 to the power of 44 positrons per second, whereas Geminga produces approximately 10 to the power of 37 positrons per second. Although this may seem like a tiny fraction of what the Sun produces, it's crucial to remember that Geminga is much smaller than our Sun. When we consider their size, Geminga emerges as a true champion of positron production. The intense energy released by Geminga causes these positrons to travel at an impressive 40% the speed of light. As they hurtle through space, these particles form a wide beam extending over a massive distance of 100 light-years. Eventually, they reach the outer reaches of this beam, where they begin to slow down. This deceleration occurs because the positrons encounter a thin gas called the interstellar medium. It's here where the interstellar medium, composed of hydrogen and helium atoms, slows them down to a crawl. But wait, doesn't this mean that the positrons annihilate before reaching Earth? Yes, you're right. Typically, when a positron collides with an electron, they annihilate each other, releasing gamma rays. So why do we detect positrons on Earth? The answer lies in the fact that the interstellar medium between Earth and Geminga is relatively sparse. It's so thin that some positrons can travel for tens of thousands of light-years without finding an electron to annihilate with. Therefore, the positrons from Geminga continue their journey, passing through our solar system and eventually reaching Earth. When they do collide with particles in our atmosphere, the resulting gamma rays can be detected by instruments like the Fermi Gamma Ray Space Telescope. This telescope has played a pivotal role in our understanding of positron emissions from Geminga. The telescope has allowed us to observe the annihilation of positrons with electrons in our atmosphere, providing direct evidence of Geminga's impact on our planet. So now you might be wondering, what happens when positrons hit Earth? As I previously mentioned, when a positron collides with an electron in our atmosphere, they annihilate each other, releasing two gamma rays that shoot off in opposite directions. These gamma rays carry a tremendous amount of energy, reaching millions of electron volts, equivalent to around 1 million times the kinetic energy of an average electron. To understand how scientists detect these gamma rays, let's turn our attention to the payload for antimatter experiments, PAMS, on board the International Space Station. PAMELA is a cutting-edge instrument designed to detect cosmic rays and antimatter. It continuously monitors the ISS as it orbits around Earth, providing an uninterrupted view of space. One of PAMELA's primary functions is to identify positrons. When a positron collides with an electron in the instrument, it triggers a cascade of interactions, producing an electromagnetic shower. PAMELA's detectors, including a silicon tungsten imaging calorimeter and a permanent magnet spectrometer, come to life. They measure the energy and trajectory of the particles resulting from this annihilation, allowing scientists to spot positrons. However, PAMELA's capabilities don't end there. It also detects gamma rays produced when positrons annihilate in our atmosphere. This dual detection capability gives scientists an unprecedented understanding of antimatter reaching Earth from space. While Geminga is the primary source of positrons bombarding Earth, scientists theorize that other pulsars and even unidentified objects might also be contributing. However, Geminga stands out as the most significant player in this cosmic game. There's a reason why Geminga is considered a unique and peculiar object. It's not just a typical pulsar. As it continues to spin at an astounding rate, it releases a steady stream of positrons, acting like a cosmic particle factory. The fact that Geminga is relatively young, estimated to be around 300 to 500 years old, contributes to its uniqueness. Its youth means that it still possesses a significant amount of rotational energy, driving the acceleration of positrons to remarkable speeds. Additionally, Geminga's small size plays a crucial role. Being smaller than many other pulsars allows it to pack a punch, releasing a disproportionately high number of positrons for its size. Finally, the alignment of Geminga with respect to Earth is a critical factor. Its beam of positrons happens to sweep across our part of the galaxy, ensuring that we receive a steady supply of these enigmatic particles. One of the most compelling aspects of studying positrons reaching Earth is the potential to learn about the matter-antimatter asymmetry in the universe. The Big Bang Theory suggests that equal amounts of matter and antimatter should have been created in equal amounts, but we know that's not the case. As antimatter and matter meet, they annihilate each other, releasing energy. If there was an equal amount of matter and antimatter, they would have annihilated completely, leaving behind only radiation. Scientists are keen on understanding why we exist in a universe dominated by matter over antimatter. Studying positrons from distant pulsars like Geminga provides a window into this cosmic mystery. Another exciting area of research revolves around the possibility of harnessing antimatter as a power source. Antimatter has the potential to release enormous amounts of energy when it comes into contact with matter. While this energy release is often seen as a destructive force, scientists are exploring ways to tap into it as a clean and efficient energy source. Understanding the properties of antimatter and how it interacts with our surroundings is crucial for realizing this potential. By observing positrons reaching Earth, scientists gain valuable insights into the nature of antimatter, paving the way for future technological advancements. Our exploration of the cosmos never ceases to amaze. Who would have thought that a star, nearly 800 light-years away, would captivate our attention so much? Geminga, the enigmatic pulsar, continues to reveal its secrets, reminding us of the boundless wonders that await our discovery. As we continue to unravel the mysteries of the universe, one thing is clear: the journey of scientific exploration is a thrilling adventure, and we're all aboard. What are your thoughts on this intriguing phenomenon? Do you find the idea of a star bombarding Earth with antimatter both perplexing and captivating? Share your thoughts in the comments below. And for more updates on cosmic wonders and scientific breakthroughs, don't forget to subscribe. Until next time, keep looking up at the stars and let your curiosity guide you through the marvels of the universe. Thank you for joining me on this journey through the cosmos. And as we continue to explore the mysteries of the universe, remember that there's always more to discover, more to question, and more to marvel at. Until we meet again in our next cosmic adventure, stay curious, keep asking questions, and never stop looking up at the stars.